I have got an interesting problem for us. Imagine that we want to get to the airport because we have a flight to catch and we want to get there as quickly as possible. So I start from this point, which I will call my house, and I will follow a route which will take me to various intermediate destinations, and maybe finally it will take me to the airport. So I'm going to draw a very simplistic view of what the real picture might look like in a real city. So these nodes in the graph might represent various intersections, and these edges which connect the various nodes might represent the different roads that connect these intersections. And let me go ahead and number these intersections. So this is the first node, which is I'm going to label as H, the home. Maybe this is the second node, maybe the third one, fourth, fifth, and this is the sixth node, which happens to be our airport. And we want to reach the airport as quickly as possible. Now, what happens when we start from our house? Is the traffic always smooth? Is it always the same time to cross any road of the same length? It's not the case, right? Because we have different amounts of traffic at different locations. So let's even take that into account in this model. So what we are going to do, we are going to give some non-negative weights to each of these edges, which will represent our understanding of how much time it takes to cross this road. So let me maybe give this some number 1, 2. So this number here signifies it takes 2 units of time to cross over from 1 to 3. I'm going to randomly give this number, maybe another 2 or 3, 4, another 1, maybe another 2 here, 3 here. Now, we have with us the complete picture. So, by the complete picture, what we mean? We know that we have to start here, which is our house, and we have to reach here, which is our destination. So, we could even go ahead and generalize this. We could call it the source and the destination, the source and the target. And these are the various intermediate paths, the intermediate locations we can get to get to our destination. And these numbers represent the amount of time that take when I get from one node to the other. Now, what's the shortest route? And the shortest route in terms of the amount of time that it takes me to get to node 6 from node 1. That's what we have to calculate. Now, obviously, the brute force approach is to find out all possible routes from 1 to 6 and just sum up the amount of time it takes to get from 1 to 6 in each route and find the route with the minimum time. But what we are looking for is an algorithm, a strategy that would work for any number of nodes and any kinds of connections between them. So maybe if we have enough time, maybe 5 minutes or 6, 7 minutes, we can spend looking at this picture that we have in front of us, and we can even probably quite simply write down all possible routes. But that's okay. That's okay for this picture, but we want a generalized solution. So let's go ahead. How do we even start solving this kind of a problem? Hmm. So, what I find best when there's no way to there's no way that we can think of solving a problem. Let's think of the simplest possible thing we can do so that we at least get some head start. So, what is the simplest possible thing we can do? Well, I know that I have to start here. So, if I have to start here, what are all the places that I can get to in just one hop? By a hop, I just mean in one traversal of an edge. So, clearly from the picture, it is clear we can get from 1 to 2 in one hop, and it will take us 1 unit of time. Or we can get from 1 to 3, and it takes us 2 units of time. So, let's maybe systematically start writing it down. So, remember, we are always starting at 1. And I'm going to write down, or rather, I'm going to tabulate all the nodes or all the intersections in this case. So I'm not writing 1 because that's the implied starting point. 2, 3, maybe I'm going to write 5 here a bit far away, and 6. So these are all the nodes in my graph. And let me create a row for this table. So here I'm going to say one hop. And what this means, in each of these empty cells, I'm going to write down the minimum amount of time it takes me to get from my source, which happens to be node 1, to this particular node. So, how much time does it take me to get from node 1 to node 2 in one hop? Well, it takes me 1 unit of time. I can clearly see it from the graph. Similarly, it takes me 2 units of time to get to node 3. Okay. How can we get to node 4, 5, or 6 in just one hop from node 1? It's not possible, right? So now you can ask me, well, you just said we want a generalized algorithm. So you asked us not to look, quote unquote, not to look at the picture. So how do we know that 4, 5, and 6 are not reachable from 1? The way we know that is by the representation of the problem. So when we are given any graph in this kind of a computation problem, how we are given the graph, how we are given this connection information is either via an adjacency list or an adjacency matrix. So an adjacency list, which I'm going to just describe here, I'm going to call it A, is just a list of neighbors for each of these edges. So for each of these nodes. So for example, for node 1, I'm given a list which just has this. So I'm going to write it down and I think it'll be pretty self-explanatory. So 3, 4, 5. And just one more. 1, 2, 4, 5. And then there are going to be some more. This is how I'm given the graph. So this capital A is a matrix, which is a list of neighbors for each of these nodes. So the first one is a list of neighbors for node 1, which just happen to be 2 and 3. And you can clearly see that from this graph. And for node 2, the neighbors are 1, 3, 4, and 5, again, as we can see from the graph. So once again, whatever is encapsulated in this graph is found out here. So that's how I know that in one hop, I can't reach 4, 5, or 6 because I refer to this matrix. So what I'm going to do, I'm going to place a symbol, infinity here. And what this just means is just that it's a very large number. 4, 5, and 6 are not reachable in one hop from node 1. So now I know, in some sense, what I've done, my algorithm has gotten this information. I am trying to spread out, so to say, spread out my limit of knowledge, spread out my information horizon, so to say. In one hop, now I know I can reach 2 and 3, and I know what are the minimum times it takes me to reach 2 and 3. Okay, now let's see what happens in two hops. Can I find this out? Again, what I want to find is for each of these nodes, what's the minimum amount of time it takes to reach each of these nodes starting from node 1 in two hops. Okay, so if I'm considering two hops, I can only go two hops from a node which I can reach in one hop first, right? So what I mean is, I'll first look at the above row. So I look at the row which has one hops and I know that I can reach 2 and 3 because these are the only ones which are marked with some non-infinity number. Okay, so I look at 2 and 3 individually and see where these guys lead me to in their one hops. So wherever I go from 2 in one hop, in essence, I'm going to that place in two hops starting from node 1. So what I mean here, and this is just to explain it pictorially, if I can reach from 2 to 4, 3, 5 in one hop, and I know that I can reach in one hop to 2, that means those are exactly the places I can reach in two hops, starting from node 1 via node 2. So let's look at those. And one thing that we want to be clear, be- because this algorithm that we are trying to find out is going to be very general. It's going to be work. It's going to be, or at least we want it to work for all kinds of graphs. So a graph like the one we have shown in the picture might have cycles. This guy has a lot of cycles. So by a cycle, we just mean a closed shape, right? It's pretty obvious what a cycle is. So we don't want to end up backtracking, and that's a real life constraint as well, right? Because in this kind of a traffic scenario and in this mathematical model, each of these edge weights are going to be non-negative. Traffic obviously will slow us down, it can never speed us up. So all of these weights are non-negative, so we never want to backtrack, because if we backtrack, we're only adding time, which goes against the very objective of the problem we are trying to solve. So now let's see. I want to see where I can reach in 2 hops. Okay, so in 1 hop, I can reach node 2 and 3. Let's start with node 2. The neighbors of node 2, as can be seen from here, are 1, 3, 4, and 5. I'm going to discard 1 because that would imply I'm coming back to 1 from 2. That's not something I want to do. So I can consider 3, 4, and 5. Let's see 3. So, how much time does it take me to reach 3 in 2 hops? Well, it does take 1 unit of time to get to 2, and it takes further 2 units of time to get to 3. So it takes a total of 3 units of time to get to 3. And in parentheses, I'm just going to write down 2 here to indicate that this is the time. This 3 is the units of time it takes to come to 3, where the penultimate node is node 2. So I'm coming, there can be other nodes, right? There can be other paths which lead me from node 1 to node 3, and my objective is to find a path, not just the minimum amount of time. So I better keep track of who is leading me to this destination node. So not only am I keeping track of the amount of time it takes me to reach this particular node, I'm also keeping track of where did I come here, where did I land here from. So in this case, it took me 3 units of time and I came via node 2. Let's move ahead. It's almost a similar calculation now. So I'm just going to do it maybe for a couple more nodes and then we'll see. So node 4. To get to node 4 via node 1, it already takes us 1 unit of time to get to node 1 and a further 2 units of time to get to node 4. So again, 3 units of time via node 2. Okay, let's see for 5. For 5, again, 1 unit of time to get to 2 and another 3. So 4 units of time coming via node 2. And again, 6 is not possible to get to in 2 hops. So I'm going to mark it infinity. And if you want to do it, if you were to actually write a program for it, you would see this because none of the neighbors for 4 and none of the neighbors for 2 and 3 would include 6. So we can't get to 6. Now, so far we have only considered node 2. What about node 3? Now let's see all the places we can get to node 3. We can get from node 3, I'm sorry, and these are all the places. Once again, it's 1, 2, 4, and 5. Okay, again we will discard 1. We're still in 2 hops, by the way. Now we're looking at all the places I can get to from or via node 3. So via node 3, I can get to node 2. Okay, and how much time does it take? Well, it takes 2 plus 2, 4 units of time to get to node 2 via 2 hops. Okay, so I'm going to say 4 units of time via node 3. And then, how much time does it take to get to node 4? Well, it takes 2 plus 4, 6 units of time to get to node 4. I can say it takes 6 units of time and I'm coming via node 3. But what I want to do, in fact, is not to write these two numbers. Because I'm only if I ever want to get to node 4, I'm only ever interested in finding the minimum amount, right? So I better not write this one because it's more than 3. If I ever want to get to node 4, I would always choose to come via node 2 because it takes me 3 units of time. So from now on, if our calculated number happens to be more, we won't write it. We will always maintain the smallest number, smallest amount of time it takes. Okay, then let's do the same thing for 5 via node 3, by the way. So we take 2 plus 1, 3 units of time. If we take 3 units of time, why should we take 4 units of time via node 2? So instead of this, in fact, I'm going to use the eraser here. Oh, it's pretty big. And then we'll jump back to pencil. So I found out a shorter route, and that's 3 units of time it takes via node 3. And again, we can't reach node 6 in 2 hops. The reason is because we were considering all the places we can get to from node 3, and node 3 is not connected to node 6. What do you think we'll do next? We will just extrapolate this. And I'm not going to do it because you know what's happening now. Now I know what are all the places I can get to in 2 hops. And those are exactly those places which are not infinity in this row. So, in a sense, I have now extended the horizon of my knowledge to two hops. So it's this information that I have covered. These are all the places that I can get to in two hops, and all of that information, in fact, all of that optimal information, the shortest time, is contained here. And again, what will I do for three hops? Well, I know all the places I can get to in two hops. I will look at their respective neighbors like we just did and write down how much time it takes to get to each of them. And also, we will write down where we are coming from. That will be the penultimate node. And I'm going to actually stop here because it's the same computation we just did. And what do you think will happen? Can we get, there will come a time we will be able to get to node 6. That might not be optimal for this case. Who knows? I don't know. I just put those numbers randomly. So we can clearly see this path, right? Which gets to node 6 in 3 hops. And where does it come from? It comes from this node. So when we are considering node 4 for filling up this guy here, one of the entries we will get is for node 6. We don't know whether it will be the shortest or not, but it will definitely fill up this guy, node 6. Now, once we have that, what do we do? Well, think about this. If you have a graph, however complicated it may be, if you have a graph with n vertices or n nodes, and let's assume that it is possible to get from one node to any other node, what's the longest path length that we can take? What's the maximum number of hops? Well, clearly the minimum number of hops is one. The target node might just be one node away. It might be your neighbor. But what's the maximum number of nodes? What's the maximum number of hops you'll have to cross? Do you realize? It's going to be n minus 1. The worst case. Because we are, and why is this? Because of the precise assumption or our stipulation, rather, that we will avoid cycles. We will never backtrack. If we avoid cycles, then the maximum path length, imagine assuming that everything is connected to everything else, is n minus 1. Obviously, if you include cycles, you can keep going around in cycles. But it's n minus 1. N minus 1 is the maximum number of hops. But now let's come back here. Look at this. What does each row signify? Each row gives us information about the amount of time it takes to get, or rather, the minimum amount of time it takes to get to each of the nodes. So this might be n columns here, and rather n minus 1 columns here, removing the source column. It tells us the minimum amount of time it takes to get to each of these nodes. And then I can tabulate the same thing n minus 1 times. And I will get all possible path informations. In fact, if it were so that um somebody asks us, okay, you calculated, or rather, you solved the problem for 6. What if I wanted to now get the minimum amount of time it takes to get to node 5? Same problem, but now my destination has moved from 6 to 5. The beauty of this approach is that, let's say you do it for n minus 1. Once you do it for n minus 1, if your graph is not changing, if your traffic situation, so to say, is static, then you have actually solved the problem for all possible nodes, or other all possible target nodes. Because let's say somebody does ask you the second problem, which is, okay, very well, you've solved the problem for node 6, but please tell me what's the minimum amount of time it takes to get to node 5. So then our approach should be, yes, let's solve this problem, or rather tabulate this information for n minus 1 rows, and then let's look at the column 5. Well, for each of the time it is infinity. We know that it is impossible to get to node 5 from node 1 in this many hops indicated by the row number. But as soon as we start finding numbers, we know that it is possible to get to node 5 in 3 hops, and we're coming via node 3. If I went further, there might be another number here. It might be lower or might be high. Why can it be lower, by the way? It could be lower because the path that we are considering via three hops might be coming via some some other path which has lesser traffic. But anyway, what we would have to then do is to come to node 5, look at this column, find out the smallest number in this column, and we claim, hey, I have, and look at, if you look at the row number, we will say then, let's say the row number happens to be k. We say we can reach 5. And the smallest amount of time it takes to reach 5 is k hops. And because I have the penultimate row here, the penultimate node here, we can even backtrack and calculate what's the exact path we took to get to node 5 in k hops. So it's such a nice algorithm. Not only does it solve the problem we ask for, it actually solves the problem what is the shortest time it takes to get from 1 to t for any target node t in the graph. That's interesting. Think about it. But there is a catch. And what's the catch? This algorithm also assumed, rather, our problem assumed that we will not be given any negative numbers on these edges. Why would that be a problem? First of all, what would that even indicate? Well, it might indicate some certain preferences in our original problem. So you do want to get to the airport the earliest, but there are certain edges you want to prefer. Maybe you have to pick up a friend from somewhere. So maybe giving a -2 here would signify that, oh, I have to go here because my friend's house is here and I have to pick him or her up. But that will not work with this algorithm. Because in general, let's say if we were to come up in this situation, I have a -2 here as well, and I'm just making this up. And for some reason, I have a -1 here. What you would think our algorithm is going to do? Because first of all, if I have negative numbers, I will not preclude cycles. And if I don't preclude cycles, I'll just keep on moving. Rather, the algorithm is going to get stuck because it's so happy. It keeps on getting negative numbers, and it thinks it's finding a path with lesser and lesser time. But that doesn't make practical sense. So maybe this algorithm would not work if we had negative weight edges. But still, I think it's a nice algorithm and I wanted to share this with you. So thank you, everyone.